All right, question 8. So what's going on in question 8 is that we're defining this random variable y in terms of some other random variable x. So x has something to do with cubic yards of cement, or I guess concrete, and y has to do with the cost, but none of that matters. All that's relevant is that y is a random variable defined in terms of x. That's all you need to know about y. So think about what this means. If you know what x is going to be, you can figure out exactly what y is going to be, right? If x were 10, 75 times 10 is 750. 750 minus 100 is 650. If x is 10, y is 650. But we don't know that x is 10. X is a random variable, right? It has a 15% chance of being 10. It has a 25% chance of being 15. Has a 25% chance of being 20, 30% chance of being 25, and a 5% chance of being 30. Turns out you don't need any of that information either. And the reason why is because they tell you the expected value of x is 1925. You can write that as the expected value of x is equal to 19.25. In other words, the mean of x is 19.25. Knowing that, we could figure out the expected value of y, although it doesn't ask you for that and you don't need that. But if you did, it would be easy enough. All we'd have to do is take 75 and multiply it by the expected value of x, 19.25, and then subtract 100. Let's see, can I do this in my head? Maybe, but I don't want to. 75 times 19.25 minus 100 gives me 1343.75. If the question asked me for the expected value of y, which I could write as mu sub y maybe, my answer would be $1,343.75. Oh look, that's answer D. But it doesn't ask me for that, it asks me for the standard deviation. And you're like, all right, I get the point. We know the standard deviation of x is equal to 5.76. So if I take that 5.76 and throw it into this formula, I'm sure it'll give me the standard deviation of y, right? No. You can either just memorize that what you do in situations like this is you take the old standard deviation and you multiply it by the coefficient here, but you ignore this minus 100. What I'm saying is the standard deviation of y is going to end up being 75 times 5.76, which is equal to $432. Here's proof of that fact. The answer to this question will end up being B. But rather than just memorize that that's kind of like how you work these problems, it helps to think about it. So recall that the standard deviation is just a measure of spread. If I can measure how spread out x is as 5.76, whatever the unit is, and then I take that x thing and multiply it by 75, I'm multiplying all the possible values of x by 75. So values of x that used to be 2 apart maybe, when I multiply them by 75, those new values are now 150 apart. All of the values of x are scaled by a factor of 75, so the distance between them is also scaled by a factor of 75. Scaling x will scale y proportionately. What about subtracting 100? Well, again, think about it. I used to have these two values that were separated by maybe 2. I multiply them by 75, now they're separated by 150. I subtract 100 from each of those values. They each get smaller by 100, but they're still separated from each other by 150. Adding or subtracting to this product is not going to change how spread out they are. It'll absolutely change their expected value, but because the standard deviation is a measure of spread, adding or subtracting to it, I think translating would be the proper mathematical word to use. But for the sake of clarity, I'll write adding or subtracting to or from x won't change the standard deviation one bit. Note that if you subtracted 100 from this value, you'd get 332, which is exactly answer A. I can see a lot of people putting this in as the answer because it's what you'd get if you kind of treated the standard deviation like you treat the mean, but you don't. If you make $10 more than me and we both take a $100 pay cut, you still make $10 more than me. Adding or subtracting to all of the values does not change how spread out they are. The standard deviation of y would be 75 times the standard deviation of x, in other words, $432.